All right, in this video we're taking a look again at a center of mass. So I've written down some formulas here. First of all, we're trying to find x bar, y bar, which is just the center of mass, the point about which all of the mass is evenly distributed. The formulas for x bar and y bar are given here. X bar is this fraction, the moment or the tendency to rotate about the y-axis divided by the mass. Y bar is the moment or the tendency to rotate about the x-axis divided by the mass. And each one of those things is calculated as a double integral. So the mass, whoops, this is take 2 of this video. I have already calculated it, but I totally flubbed the video. So we'll just pretend that answer is not there. Okay, the mass is just the integral of the density function. The moment about the x-axis is the integral of y. Y is the distance from the x-axis, sine distance from the x-axis times density. And the moment about the y-axis is the double integral of x times the density. Okay. So notice, in the formula for x bar, the symbol with a y shows up on top, but that's the integral with an x in it that's showing up on top. Okay. You will also notice that in order to find just this one point, we've got to do 3 integrals. Now, there are some ways that I can make that more manageable on an exam. One is I can ask you to find just the x value or just the y value. That cuts things down a little bit. Another thing I can do is I could give you a lamina that's homogeneous so that the density function is constant. When that's the case, we call the center of mass the centroid. But it's kind of nice because to find the mass, it's just going to be the area of your shape times that constant density. And if your shape is something nice like a disk, it's just pi r squared. You don't need to integrate at all to find that. This problem, on the other hand, we got to integrate. Okay, so here's our lamina. It's the region between y equals 1 minus x squared and the x-axis. And the density function is k times y, where k is just some positive constant. Okay. Now, here I gave you the formula. You're going to encounter in the homework, you're often going to be told that the density is proportional to something. Okay. So what this equation means is that the density is proportional to y. When two things are proportional, one is a multiple of the other. So you want to make sure you understand how to translate from the verbiage of this is proportional to that to this is k times that for some constant k. All right, so let's find these things. I'm going to start by finding the mass. I'm just going to work my way through in order. So the mass is the double integral over d, we'll just call this region d, of the density function, k times y, dA. So I need to decide how I'm going to slice d up. Looks like we were given a formula for the top boundary, and the bottom boundary is just y equals 0. So I'm going to slice things this way, and notice that this parabola would intersect the x-axis at -1 and 1. So we're going to integrate from -1 to 1. That's going to be my dx. That's telling me where the slices start and where they end. The outer limits of integration are the extreme, in this case, left and right. The inner limits of integration, which are going to be my y values, are going just from the bottom to the top of the slice. So from 0 to 1 minus x squared. Common mistake is people say they're going from 0 to 1 because they say, oh, we got to go to the top of the object. No. The outer limits of integration deal with the object as a whole. The inner limits of integration deal just with that slice. And not all slices go all the way up to 1. Okay, and then we're integrating k times y. All right, k is a constant. I don't know what it is, but I'm going to factor it out. I'm suspicious, by the way, that k is just going to show up in the top and bottom of these fractions so that it's going to cancel. But let's keep it in there. It can just hang out. Okay. So then we're integrating from -1 to 1. And let's see. Antiderivative of y with respect to y is going to be y squared over 2. And that's evaluated between 1 minus x squared and 0. And then we still have to integrate that with respect to x. I'm going to go ahead and pull that 2 out. So this is going to be k over 2 times the integral from -1 to 1 of, let's see, I'm going to square this, so that's going to give me 1 minus 2x squared plus x to the 4th, minus, when I plug in 0, I get just 0. And so we're integrating this with respect to x. Now, if I want to, I can make my life a little bit easier here. I'm noticing that that's an even power, that's an even power, and even that is an even power. So if I look at it, this shape, my lamina, had some nice symmetry to it, in that the left side is just a mirror image of the right side. Now, if I look at mirror image points, the integrand 1 minus 2x squared plus x to the fourth here, I'm going to get exactly the same value at the mirror image point here, because the x values of these points are exact opposites, but when I take them to even powers, they're going to be the same. So what I can do is just integrate the right half and then double it. That's going to make it a little bit nicer, because then I get, as my lower limit of integration, 0 instead of -1. So I'm going to say this is 2 copies of k over 2 times the integral from 0 to 1, just taking advantage of the symmetry, 1 minus 2x squared plus x to the fourth dx. Really important if you are using symmetry, it's not enough that the shape is symmetric. Mirror image points have to have the same value for the function that you're integrating. Okay. And if you're not sure, I would just keep the limits the same and just work it out. Okay, I'm going to cancel those 2's, and then I'm going to erase some space. Erase some space. I'm not erasing the space. I'm going to make some space by erasing some stuff. Okay, so we'll just bump up to the top of the board here. So I've got k copies of, now we're just integrating this with respect to x. So that's going to be x minus 2x cubed over 3 plus x to the fifth over 5, and that's all evaluated between 1 and 0. So that's going to be k times 1 minus 2/3 plus a fifth, minus, when I plug in 0, all of these terms go to 0. So that's k times 15/15 minus 10/15 plus 3/15. That's going to be k times 8/15. So the mass is 8k over 15. Excellent. Okay. So next integral I'm going to find is m sub x. Okay. If you want, feel free to pause the video and work this out on your own. I'm going to work it out in the meantime. When you come back, you can either watch my explanation or just check that you got the same answer that I did, and then sort of fast forward through the explanation. I would encourage you, though, there's a nice shortcut when it comes to finding m sub y. So if you wanted to work all the way ahead to find all of these, think before you integrate for this one. There's a nifty shortcut and it's a big time saver. Okay? So feel free to work these out on your own and just check your answers, or keep playing along with me, whatever works better for you. Okay, so m sub x, the moment about the x-axis, we're told is the double integral over d of y times our density function, which was ky dA. So again, I'm just going to factor out the k, and my limits of integration, same region, so it's the same as last time. Once I've done that once, it's going to be the same, but now we're integrating y squared dy dx. So I'm going to get k times the integral from -1 to 1, y cubed over 3 evaluated between 1 minus x squared and 0, and then we still have to integrate that with respect to x. Okay. I'm going to go ahead and pull out the 3, so this is going to give me k over 3 times an integral from -1 to 1, and now I've got to cube this thing. Okay. I could use the binomial formula if I wanted to. I'm just going to multiply this one out, 1 minus 2x squared plus x to the fourth. We'd already squared it, and then times 1 minus x squared. So I'm going to distribute the x squared. So I get -x squared plus 2x to the fourth minus x to the sixth, and then plus a 1 and a minus 2x squared and an x to the fourth. So it's a 1 minus 3x squared plus 3x to the 4th minus x to the 6th. dx. So that's, oh, and let's see. I can use my symmetry argument again, okay? Because if I take a look, here was my region. Here are my mirror image points. Because it's all even powers of x that are showing up, I know I'm going to get exactly the same thing for those mirror image points. So I can say I'm going to double k over 3 times the integral from 0 to 1 of 1 minus 3x squared plus 3x to the 4th minus x to the 6th dx. Okay, so that's going to be 2k over 3 times x minus, that's kind of nice, 3x cubed over 3 is just x cubed, plus 3x to the 5th over 5 minus x to the 7th over 7, all evaluated between 1 and 0. So that's 2k over 3 times 1 minus 1 plus 3/5 minus 1/7. Oh, those 1's cancel, so that's 2k over 3 times, let's see, this will be 21 35ths minus 5 35ths. So that's 2k over 3 times 16 35ths. Yeah, that works. 16 35ths. So that is going to be 32k over 105. Very exciting. You'll notice there is a k in both of these, so that when I do take this fraction to find my y bar, they're going to cancel out, which is what we expected. Okay, so that's m sub x. Let me erase and we'll talk about finding m sub y. Okay, so m sub y is the double integral over d of x times the density function dA. Okay. I can factor out the k, xy, dA. Okay, now I'm going to use symmetry here. My region was nicely symmetric, so that the left side and the right side was much more symmetric than this particular shape. The left side was an exact mirror image of the right side. Okay. Now if I look at mirror image points, and I look at my integrand, these 2 points are going to have the same y value but the opposite x values. That means that when I integrate, if I call this the z value, the heights or the z values that I'm attaching to those points are exactly opposite. Positive here, negative here, they're going to cancel out. This is 0, just by the symmetry of that. So I didn't have to integrate in order to get that. Now I could have worked out the integral, it would have worked out to 0, but that's a really, really nice shortcut. Okay. So when you're finding centers of mass, that's one place where very often symmetry can help you. We used it actually in all 3 of these integrals. Here we used symmetry to say mirror image points had the same value, so we could just integrate over the right half and double it. Here we said, I don't have to integrate at all. Left and right half map to opposite values, and so that's just going to cancel out. Very, very nice. Okay. So now I can figure out what x bar and y bar are. So x bar is 0 over the mass, which is just 0. And y bar was m sub x over the mass. M sub x was 32k over 105. Dividing by the mass means multiplying by its reciprocal, so that'll be times 15 over 8k. As anticipated, those k's cancel. 8 goes into 32 4 times, and 15 goes into 105 7 times, I believe. 15 times 7, yep, goes in. Excellent. So we get 4 sevenths. So our center of mass, x bar, y bar, is 0, 4 sevenths. I'm just going to do sort of a common sense check. That's right around there. Seems fairly reasonable. It's higher than part way up because our density function, remember, we were proportional to our y value. So the stuff up top where the y values are higher is going to be more massive. Okay, excellent.